video, we defined the derivative for a vector function. I've just put up that definition here again. It's the limit as h goes to 0 of this expression, which just gave us a direction vector for a secant line, so that the derivative gives us a direction vector for the tangent line. And I've shown you over here that we can use the same notation for vector functions that we use for derivatives of real valued functions. So I can use the prime notation. I can write dr by dt. That r still has a bar over it because it's a vector function. Or I can write d by dt. That's the operator that tells me I'm taking the derivative with respect to t. And then I just put r of t after that. That's the thing I'm taking the derivative of. Okay. Now, when you first learned derivatives of real valued functions, you spent some time using that limit definition, and then you learned a bunch of shortcuts. Well, we don't need to use this definition. We can go right to the shortcuts. If I look at all of the work that's involved in calculating this, everything is done component-wise. When I'm subtracting vectors, I subtract the x components and the y components, and in 3-space the z components. When I'm scaling by the reciprocal of h, I scale each component. And we learned in the last section that when I take the limit of something, I take the limit component-wise. So, Theorem 2 is going to tell us that we evaluate derivatives of vector functions component-wise. And I want to just take a look at what that looks like by working through an example. Okay. So let's let r of t be e to the 2t sine t t squared. Okay. And I would like to find the tangent line when t is equal to 0. Okay. So we're going to do a little bit more than just find the derivative, but of course in finding a tangent line, part of that involves finding the derivative. Okay, so if I'm looking for a tangent line, of course I need two things. I need my starting point, which in this case would just be the point of tangency, and then I need my direction vector, which is going to be the derivative at that point. Okay. So for my starting point, that's just going to be r at 0. So I'm just going to plug in 0 to this function. So that's going to give me e to the 0 is 1, sine of 0 is 0, 0 squared is 0. So my starting point is 1, 0, 0. And then I need my direction vector. And the direction vector for a tangent line is just going to be the derivative evaluated at the point of tangency. Okay. All right, now finding that is a two-step process. I first of all need to find the derivative function r prime of t. And that's where I'm going to apply Theorem 2 and take the derivatives component-wise. I usually won't take the time to write this out, but since this is our first time taking the derivative, the component that I get in the x position is going to be the derivative of the function that gave me my x component. In the y position, I'll have the derivative of sine t, and the derivative of the z component goes in the third position. All right, so that's just 2e to the 2t cosine t 2t. Okay. Now, ordinarily, I wouldn't bother to write that I'm taking the derivative of each component. I would go right to here, and you're more than welcome to do that. Okay. Now, do be careful. That's the derivative function. My direction vector is this function evaluated at 0. So we'll have r prime of 0 is equal to 2, 1, 0. So then if I want to get my line, okay, now I want an equation for the line. So I know the formula is starting point plus t times direction vector. That's basically going to tell me what goes on the right-hand side of the equal sign. I'm going to have that it's equal to my starting point, 1, 0, 0, plus t times 2, 1, 0. but it's got to be equal to something. I've got to just give a name to that tangent line. I can name it almost anything I want. I can't call it r, because that was the original curve. I can't call it r prime, because that's the function that gives me the derivative. And that's not a linear function. Okay? I'm just going to call it L of t, because it's a line. Okay? Do be careful. Sometimes people remember the formula, but they forget an equation has to have an equal sign, and therefore it has to equal something. And so you just give a name to the function. Okay? Other thing to be careful about is I sometimes see people try to plug in the derivative function as the direction vector. I don't know of any lines that have exponential functions and cosines as part of their formula. The direction vector needs to have numeric components, so you do need to remember to evaluate the derivative at the point of tangency. All right, so there is our tangent line. And as we said, this gives us a direction vector for the tangent line. So we focused so far on the meaning of the direction of the derivative vector. In the next section, we'll get a little bit more information about what the magnitude of the derivative vector tells us. But we can start to get a sense of that if we look at a particular example. If I were to let r of t be my position function, so I've got some particle that's moving through space, r of t is describing the position as a function of time. Well then, r prime of t, I know what the derivative of position is supposed to be. It's supposed to be velocity. So I might even call it v of t. That would give me my velocity. Now that's a vector. It has magnitude and direction. But with this application, I understand what both of those mean. The direction is just the direction that the object is moving in at that time, and the magnitude of velocity is speed. And I could write that as either the magnitude of r prime of t or the magnitude of v of t, but it's going to be the speed with which the particle is traveling at that instant in time. So at least with this particular example, when r of t represents a position, we can understand what the magnitude of the derivative means, and we'll see how that generalizes to other types of functions when we get to the next section. There may be times when I really want to focus just on the direction in which something is changing. If I'm talking about a position function, then I usually do care how fast it's moving. But if I'm just trying to study the geometric properties of a curve, I might care just about the direction in which it's changing rather than how fast we're moving along that curve. In that case, I might want what's called t of t. It's a capital T with a bar over it, of t, and that's the unit tangent vector. That is just r prime hat. It's the derivative vector normalized. We preserve the direction, we stretch or shrink it to make its length 1. That will be possible anytime the derivative is not 0. Now it is possible for the derivative to be 0. Of course, if the derivative is 0, that would mean we actually don't get a tangent line because we wouldn't have a direction vector for our tangent line. But if the derivative is non-zero, we can normalize it. And of course, this is just r prime of t scaled by the reciprocal of its magnitude. And we'll use this when we're primarily concerned with the direction in which things are changing and are less concerned about how fast things are moving or how fast we're moving along the curve. Let's just try an example of calculating that. Let's suppose that r of t is 3e to the t, 2 cosine t, 3 sine t. And I'd like to just find t of 0. That would be the unit tangent vector at 0. I'm going to suggest you pause the video and try and work that out real quick and then tune back in. Welcome back. So if I want to find t of 0, first thing I'm going to do is I'm going to find r prime of t. So that would be 3e to the t negative 2 sine t, 3 cosine of t. Now, if I want to find t of 0, I've got two more steps to do. I've got to plug in 0, and I've got to normalize things. And I can actually do that in either order in this case. When I'm plugging something in, very important that I take the derivative first. If I plugged in 0 first, I'd have a constant function and the derivative would be 0. So I have to take the derivative before I can plug in any number. But it's totally fine to plug in 0 and then normalize. I could normalize as is. If I wanted a generic formula for the unit tangent vector at an arbitrary point, I'd want to do that. But if I only care about the unit tangent vector at this point, it's going to be a lot simpler if I plug in 0 first so that I'm working with numbers instead of functions. So r prime at 0 would be 3, 0, 3, and then I can normalize that. So the magnitude of r prime of 0 is the square root of 9 plus 0 plus 9. So that's the square root of 18, which is 3 root 2. So then, I'm sorry, that's not r prime, magnitude of r prime of t. That was the magnitude of r prime of 0 was 3 root 2. And then t at 0 would just be r prime at 0 normalized. So that's going to be 1 over 3 root 2 times 3, 0, 3. And I'm going to go ahead and do that scalar multiplication. That's going to simply become 1 over root 2, 0, 1 over root 2. And it's a very quick check to confirm, if you want to, that that is in fact a unit vector.